A Poisson process, it could be given, it's defined as the number in T1, T2 of all the points of Ti in the interval of that T1 and T2. The length is a Poisson random variable, lambda t. The probability distribution is given by P of n of T1 and T2 is equal to K, so the probability that's equal to K is equal to e to the negative lambda t multiplied by lambda t to the K over K factorial. Now, if the second property is if the intervals T1, T2, and T2, 3, T4 are non-overlapping, then the random variables are independent. So the first order probability masses is P x of t is equal to K is equal to is equal to e to the negative lambda t times lambda t to the K over K factorial. So the mean of this process is lambda t, and the autocorrelation is given by this, which is if T1 is greater than T2, it's equal to lambda t minus lambda squared T1, T2. If T1 is less than T2, it's lambda T1 minus lambda 2, T1 to T2. There should be a squared there, actually. So the second one is actually lambda 2 squared. The autocovariance is given by lambda times the minimum, whichever one is smaller, T1 or T2. And this behaves as we would expect. Basically, the longer time goes on, the more instances of this occur. So the second one is Poisson increment process. It's given by y of t is equal to x of t plus epsilon minus x of t over epsilon, given that x of t is a Poisson process. So the first order probability masses is given by this, which is the same except for instead of k you give n, and the probability of y of t is equal to n over epsilon, and this is lambda epsilon instead of lambda t. This brings our expected value to be a constant, which is lambda, and our autocorrelation to be as shown here, given those constraints. And you get your covariance here 0 if the absolute value of T1 minus T2 is greater than or equal to the epsilon, and it's equal to this here if it is less than epsilon. So the Poisson impulse process, that's given by z of t is equal to derivative of x of t with respect to t, given x of t is a Poisson process. The probability distribution is undefined. The expected value is equivalent to lambda. Autocorrelation is given by lambda squared plus lambda times the impulse of T1 minus T2. The covariance of T1 and T2 is equal to lambda times the impulse of T1 minus T2. The semi-random telegraph signal, it's Poisson, this is the Poisson process here, except for you define this x of t is equal to 1 if k is even and negative 1 if k is odd. This is similar to a couple homework problems we had in the past. So the first order probability masses, you're given this, and again we have derived this previously before in homeworks and in the textbook. And you get the same for x of t is equal to negative 1, with the exception of you have a minus sign, so it's e to the lambda t minus e to the negative lambda t. Expected value is e to the negative 2 lambda t. Autocorrelation is equal to e to the negative 2 lambda times the absolute value of t1 minus t2. Covariance is given by this. Random telegraph signal, so that's y of t is equal to alpha times x of t. So the probability of alpha equal to 1 is equivalent to the probability of alpha equal to -1, which are both equal to 1/2. So x of t is a semi-random telegraph signal, which is described up here. So the first order probability masses our probability of y of t is equal to 1 is equivalent to the probability of y of t is equal to -1, which is both equal to 1/2. The expected value is 0. Autocovariance is given by this, and autocorrelation is given by this, autocovariance is given by this, and those two are equivalent. The random walk. So if you toss a number of fair coins n times, and k is equivalent to the number of heads, so you get x of t is equal to k s minus n minus k multiplied by s, which gives 2k minus n all multiplied by s. So the probability is equivalent to this written here. I'm running out of time, so is that. The expected value is equal to 0. The autocorrelation is the minimum of m and n times s squared, which is equivalent to the covariance. The final one is the Wiener process. WT is the limit of x of t, given that x of t is the random walk. So the first order density is given by this formula here. The expected value of 0, the autocorrelation is the minimum of t1 and t2 multiplied by alpha, and the covariance is the same.